Okay, number 2, starting with part A, assume the following questions based on the graph shown below. Assume that all critical points of discontinuity, and the end behavior of f can be observed from the graph below. Asymptotes are indicated by dotted lines. So give a numeric value for each of the following, or write d and e if the function does not exist, or positive or negative infinity. So we're going to be going a little bit quick through these. So first one, we have the limit as x approaches -3. So here we have -3. We approach this point here, which is 2. So our first answer is going to be 2. Next, we're saying, what is our second derivative of f evaluated at x equals -4.7? So we're looking maybe somewhere around here. We just need to figure out our derivative here, which is our slope of this line here. Or, well, not our derivative, our second derivative, right? Which is going to be the concavity. And since we have a linear line here, our second derivative is just going to be 0. Just to reiterate that one more time, our first derivative is constant here, which means if I take the second derivative of a constant, take the derivative of a constant, it's going to be 0. So that means our second derivative for this area is 0. Next one, we're going to be taking the integral from -8 to -6 of f of x dx. So we're going to be sort of calculating this area in here. And we can see that it's a nice square. So we just use basic geometry and we say, okay, our width is 2, our height is 2. So if we integrate this, we're going to get 4. So next we're going to find our derivative at 5.4. So we see 5.4 is maybe somewhere around here. So we're looking for a slope of this line here, which we see we go up 2 in one step. So our derivative or our slope is 2 here. If we approach -4 from the left, what is that value going to be? Okay, well, here's -4. If I approach it from the left, I follow this line here, and I get to this point here, which tells me that the limit there is going to be -1. Okay, for this next one, we're going to be taking the average slope over this interval as we approach 4. And since we're taking the limit of this, as this interval gets smaller and smaller around 4, we're sort of looking for the derivative right at 4. And right here we can see that we're sloped our slope is 0 right at that point. So that means that we can evaluate this to be 0. Next, we're saying, okay, what is our derivative as x approaches 6? Okay, so if I look at 6, what is my derivative or my slope here? Well, here my slope is 2, and we have this discontinuity here, but our slope remains the same. So we're not going to have any sort of real issues there with saying that our slope as we approach that point 6 is going to be 2. Okay, next we're going to take the derivative of the integral from -2 to 1 of f of t dt. So the first thing worth noting is that if I integrate something from -1 to 1 of f of t dt, it's going to be some constant, some number, right? It might be 3, 4. It really doesn't matter what it is, because if I take the derivative of that with respect to x, it's going to go ahead and be 0. So you don't even have to find any area, because we know it's going to be some constant. If I take the derivative of that constant, it'll be 0. So this last one, we have a summation formula, and these are all just going to be some Riemann sums, or ways to sort of help think about integrals. So what this is saying is that we're going to have some width portion here that's going to be constant, and it's going to be 1 over n, and we're going to make that width infinitesimally small. Then we have some height here, which is represented by this. So you can see that we're evaluating this from 5 to something, right? And because this here, if we look at our equation, this is b minus a is represented by this. b minus a over the number of rectangles that we have. So because of this, we can say that our overall interval is just going to have a width of 1. And we can also see that because of this number here, we're starting at 5. So what we're doing is we're approximating our area from 5 to 6 using a summation formula. So if I look here, though, my area from 5 to 6, well, this is just going to be a nice triangle here with the height of 2 and a base of 1. So if I go ahead and just calculate the area of this triangle, it'll be 1, which should line up with our summation formula for this Riemann sum. Okay, so for this next one, part B, we're going to identify a value c from -5 to 5, such that f is discontinuous at x equals c, but the limit exists. So if I go from here So I can see here we have some issue, right? We're not continuous, but our limit also does not exist because it approaches two different values. Right here, I can see I'm discontinuous right here because I jump up to this. You can see my limit does exist though. So we can go ahead and say that C is going to equal -3. Let's just go ahead and double check if there's any others. So my next point of discontinuity would be right here. But again, my limit doesn't exist because I approach two different values from the left and right. Okay, so for our next problem, number 3, starting with part A, we're going to evaluate the following limits or state if they don't exist. Numbers alone without any justification or theorems will receive no credit. If you use L'Hopital's rule, clearly indicate when you do so. So we have the limit as x approaches a from the left of 2 times x minus a over the absolute value of x minus a. So these absolute values can be a little tricky, but a good way to approach these is to sort of separate the positive and the negative version and sort of look at it from as maybe like two different functions almost. So what we could do is say that for whenever x is less than a, that our absolute value of x minus a, x minus a is going to be the same thing as the negative of x minus a. And a good way to double check this is just try plugging in a number. Because let's just say, for example, x is 4 and a is 5. So 4 is less than 5. So I know that the absolute value of 4 minus 5 should be positive 1. So let's double check that this formula here works for those values. So 4 minus 5 times -1, there we go. That's going to be a positive 1. So because that works, we can also write out the other portion whenever x is greater than a, the absolute value of x minus a is going to equal positive x minus a. And you can double check this the same way we did before by just thinking of two numbers, x and a. So because we approach the value, or x approaches the value of a from the left, that means that x is going to be less than a, which means that we have to follow this formula here because we approach from the left. Because we approach from the left. So because we are approaching from the left, we're going to use this formula. Approach from left. So if I go ahead and just imagine plugging in this here, now we have that our limit as x approaches a from the left is going to be 2 over x minus a over negative x minus a. So from here, we can go ahead and say, well, our x minus a's are going to cancel out, and we're just going to have that this here equals 2 over -1 or -2. And that's going to be our answer for this one here. Okay, moving on with number 3, part B, we're going to take the limit as x approaches 1 from the right of x plus 1 over x squared minus 1. So first thing to notice is if I try evaluating this right off the bat by just plugging in 1, I'm going to get 2 over 0, which we can't have that, right? So because we don't want to have this undefined portion in our denominator, or well, a 0 in our denominator, let's see if we're able to do anything to simplify. So if I go ahead and notice that this is a difference of squares right here, what we can do is say that this is going to be x minus 1 times x plus 1. So now I can see that I can actually just take this 1 here, or this x plus 1, and cancel those out, and now say that this is going to be 1 over x minus 1. This still doesn't quite help us though, because if we notice, if I try evaluating this as x approaches 1 from the right, my limit still isn't going to exist, right? So if I do my limit as x approaches 1 from the right, I have 1 over x minus 1. This here is still going to diverge. So our value here is just going to be, we can go ahead and say that it does not exist. Or if we approach 1 from the right, this will be some really, really, really small number, and it'll be positive. So this here would go kind of approaching towards infinity. So either one of these should work. So let's just go ahead and say d and e or infinity. So for this next one here, part C, we're going to take the limit as x approaches 0 from the right of cosine of x minus 1 over the square root of x. So firstly, let's just try plugging in 0. So I'll have cosine of 0 minus 1 over 0. So right off the bat, we should have some alarm bells ringing because we don't want a 1 over 0. But if I go ahead and simplify this sum, I see that I'm getting 0 over 0. So 0 over 0 is an indeterminate form. So because this is indeterminate, we can apply L'Hopital's rule. So if I go ahead and apply L'Hopital's rule to this, my new limit is going to be the limit as x approaches 0 from the right. So if I take the derivative of my numerator, the derivative of cosine of x is going to be negative sine of x. And the derivative of 1 is going to be 0. And then my derivative of the denominator, the square root of x, is going to become 1/2 x to the negative 1/2. So I'm able to simplify this a little bit. Let's say that we have the limit as x approaches 0 from the right of 2 times the square root of x times sine of x. And this will also be negative. So now if I try evaluating this as x approaches 0, notice from the right as well. Sorry, this here isn't undefined. Then this here is just going to equal 0, and that will be my final answer. In number 4, starting with A, we're going to compute the following derivatives, and it says explicitly, do not simplify your answers to part A and B, and your answer to part C should just be a singular number. So starting with A, notice that we kind of have like a chain rule here. We have some inside function, which is that secant squared of x. So first thing that I need to do is say that g prime of x, my derivative, is going to be, so if I take the derivative of natural log, I have 1 over my inside, which in this case is secant squared of x, and then I multiply that by the derivative of that inside portion. It's the derivative of secant squared of x. So we need to figure out what the derivative of secant squared of x is now. So the derivative of secant squared x, we kind of have to do another chain rule for this here. So we can go ahead and say that g prime of x is going to equal 1 over secant squared of x times, so since I have something to a power, we can pull that power down, then multiply it by our inside to whatever our new power is, which is just to the first, and we multiply that by the derivative of the inside. So now I just have to take the derivative of secant, which is going to be secant of x times tangent of x. And normally it'd be a good idea to go ahead and simplify, but since it tells us explicitly that we don't have to simplify, we can go ahead and say that this here is our final answer and be done with this part.
So for the next one, I'm asked to find the second derivative of this. So let's write y prime. So I'm going to need to use chain rule. The outside function is e to the stuff, so it's going to be e to the 1 over x times the derivative of 1 over x, which would be, well, let's think of that 1 over x as x to the minus 1. And then the derivative of that will be negative 1x to the minus 2. And so if I write that out, that will be negative e to the x to the minus 1 times x to the minus 2. Now if I want to take the derivative again, I will need to use product rule. So let's take the derivative of this part first. So the derivative of that will be negative e x to the minus 1 times negative x to the minus 2 times, I'm going to leave the second part alone, so x to the minus 2 plus, so this here is the derivative of the first times the second, plus, now I'm going to leave the first one alone, negative e to the x to the minus 1, and then the derivative of the second. So that's going to be negative 2 x to the minus 3. So that's the second derivative. So for this next one, you just kind of note that there is a error here with the variable. So that starts out f of theta, so this should be a theta, and this should be a theta. Okay, and then it's asking to compute f prime of pi over 2. So if we want to do f prime of theta, the derivative of sine is cosine. The derivative, and leave the cosine alone, plus leave the sine alone, and then the derivative of cosine is negative cosine. Okay, and so f prime of theta is equal to cosine squared theta minus sine squared theta. Okay, and if I want to do f prime of pi over 2, I'll put in f prime of pi over 2. So that's cosine squared of pi over 2 minus sine squared of, pi over 2. Okay, and cosine of pi over 2 is 0, and sine of pi over 2 is 1. So it should be negative. So it should be 0 minus 1 squared, which is just minus 1. Okay, now it says evaluate each of the following. So I'm going to evaluate these integrals. So this is integral of 10x to the 7th. So actually, let's see here. I want an antiderivative of this. So for an antiderivative of 10x to the 7th, the 10 is going to stay put. I'll have x to the, since I'm taking the antiderivative, the power goes up by 1, and I divide by the new power. Minus, and then 16 can stay put. And then an antiderivative of 1 over x is natural log of absolute value of x plus c. Okay, for this next one, I'm going to need to do a u substitution because I can see that I have a composite function and the inside part is t cubed. So I'm going to let u equal t cubed. Then du is going to be 3t squared dt. So I can divide that by 3. I get 1/3 du is equal to t squared dt. So then I can rewrite my integral to be cosine of t cubed times t squared dt. And that gives me integral of cosine of u times 1/3 du. I can pull the 1/3 all the way out. Cosine u du. And an antiderivative of cosine u is sine of u. And then I can go all the way back to t's. So 1/3 sine of t cubed plus c. All right, for the next one, I need to, again, do a substitution. Oh, no, wait. I can't do a substitution because I don't have an extra theta, but I don't need to because this is actually a fundamental theorem of calculus part 2. So I'm going to employ fundamental theorem of calculus part 2. If you don't remember what that says the derivative of the integral of f of t dt is going to be equal to, from a to x, is going to be equal to f of x. And I'm going to actually include this with the chain rule as well. So here's how they intersect. The integral from a to g of x, f of t dt, is going to be f of g of x times g prime of x. So there's the fundamental theorem of calculus part 2 using the chain rule. So when one of these bounds, when this bound is not just an x, it's a function of x, I need to use the fundamental theorem of calculus part 2 mixed up with the chain rule. So this is going to be equal to sine of 2x squared times the derivative of 2x, which is just 2. So that's the answer for that one. For this one, I'm going to try a u substitution. If I let u equal square root of x, which is x to the 1/2, then du is equal to 1/2 x to the minus 1/2. Or in other words, that's 1 over 2 root x dx. So then I can have the integral of 5 to the u. Okay, so 1 second. I can multiply this by 2, and I get 2 du is equal to 1 over root x dx. So then this is 5u times 2 du. I can pull the 2 all the way out. And I also need to convert my bounds to u bounds. So if I know that u equals square root of x, then when x is 1, u is square root of 1, which is 1. And when x is 4, u is square root of 4, which is 2. So this goes from 1 to 2 when I convert to u bounds. And so then the integral of 5 to the u is going to be 5 to the u divided by natural log 5 plus c. And if I go back to x's, oh, sorry, actually I don't do a plus c because it's a definite integral. So I can plug in from 1 to 2. So that's going to equal 5 squared over natural log 5 minus 5 to the first over natural log 5. So you can put that in your calculator and get a decimal approximation of that if you like. Okay.